Okay, so we left off right here. This is not too important. We just kind of go down here. So we do this quick derivation where it says 2.2 from the total differential. Yeah, so let's just kind of see what we understand here. We can use the total differential, 2.2. They just wrote it above. We don't really have to review, but 2.2 is referring to 2.2. So the 2.2 is just equation 2.2 is the total differential. Yeah. So we can use the total differential 2.2 to write a simple formula for the slope of the level curve. If we take any 2 points on the same level curve, by definition, they yield the same y. Hence, the delta y equals 0. We just want to put this in an incredibly simple language. So I'll kind of read their little paragraph here. I always kind of repeat the same thing twice, maybe. I kind of do my description, then we read it, and we just do the description again. Yes. Um, but what happens here? So the delta y, this is true. This is not anything new. That right there is just going to be the total differential. That's what that statement is the total differential. Yes. We can see in our head, what if delta y? Yeah, now delta y is literally how much we go up or how much we go down. That's what the total differential is. It's not approximate, I don't think, maybe approximate. It should be exact, but it's the approximate or the exact amount that we go up or down. So what if one of these is the same as the other one, except of course negative? If the magnitudes are the same, the numbers are the same, except one is negative. Uh, so with one of these, we said that's the amount that we go up or down. Yeah, that's the change. And that's the change that we go up or down. Well, what if they're the same, except one positive and one is negative? Then we don't go up or down. We're at the same level that we were before if one equals the other, but one's positive, one's negative. Yeah. So it's not really an understanding, but we take the total differential when on the same level curve, I guess. We take the total differential and just set it equal to 0, yes? And then, we solve for it. And one is the negative of the other. If it's negative, it's now they now equal or something. Yes. But so we're just going to go ahead and say it twice. So we have the total differential for the level on the same when on the same level curve, yeah, as we had below the same contour. If you have an actual mountain, it's a contour. If you have one of our simple graphs, they're just level lines. But if we're on one of our contour lines, just one, then the total differential is always going to equal 0 on that contour line. Yeah. So that's obvious. Because we want to find the maximum later. What is the whole point? It takes, many videos to get to the point, but we use the total differential. And this comes from 2.4, it comes from the total differential. We use this for optimization is what we use it for. Um, so one of the contour lines, let's just kind of make the quick point. We can scroll up if we want in the book, but we have these contour lines, yeah? If we're on a single contour line, this is x2 and this is x1. It's kind of like we get confused, but it's the same as y equals mx. This right here, this x2, that is a slope formula. Yeah, it's not kind of. Yeah, that's the exact slope formula. That's y, the change in y2 minus y1 over x2 minus x1, but it is x2 and x1, yes. But it is x2 as a function of x1, yes, but that right there is the slope formula. So let's just kind of get to the point. We're on the same contour line, and what this does is it gives you the slope to that contour line. They're telling us, yeah, the slope, the rise over run or the negative rise over run. This equation just gives you the slope. That's all it gives you there. But they are telling us something, so we want to define this. Yeah, this right here is the slope. Yeah, so it is the slope. The top right here is the partial derivative. Yeah, it's the derivative of f with respect to x1. Yeah, and this right here is the partial derivative, the partial of f with respect to x2. Yeah, so if you take the partial of 1 and you take the partial of 2, and you have a negative in front of it, there's not much of an intuitive definition. They just give us the equation there if we analyze it. So you take the partials, you have your y equals, what was y? You know, I'm just making one up here, but 4x1 plus 8x2, I think that is what it was, but it doesn't matter. We can kind of quick do that exercise. In fact, let's do the exercise if we scroll up. Yeah, so it is y equals 4x1 plus 8x2. Yeah, so they're just telling us that we have this special equation for the slope of this line. It's actually, I'm sorry, not that. What do we have here? We have one contour line. We have to choose a height. Yeah, we have to choose a height where our contour line is. Yes, we have this guy right here. Okay, good. Yeah, so let's kind of write that. I got a little bit confused, so I apologize. Okay, so the partial of y with respect to x1 equal 4. Yeah. The partial of y with respect to x2. And on a more complicated graph, obviously they are functions here, they are not, is 8. So be careful with this little thing right here, yeah? It's just an equation. We care about the derivation and it's obvious, but it's not really intuitive. X2 up top, over here x1 is up top, so they're kind of flipped to each other, yes? But it is going to be negative the partial of x1, which is 4, over x2, which is 8, yeah. So the slope is negative 1/2. Now it tells you something there, yes, because it wasn't a mistake at all, but before I chose a contour line, which we don't really want to do, what is the thing? Yeah, it's going to be the slope for all contour lines, and we already know that if we scroll up, all the contour lines, it doesn't have to be at height equals 80, it can be at height equals anything. For this very easy example, all contour lines have the exact same slope. They're parallel, they all have negative 1/2. If they change, then this thing, because it's not for the 80, it's for all contour lines that exist there. Yes. So if you have a more, complex function, maybe the Cobb-Douglas, but if you have, we don't have much in this class that's very, what do we call it, difficult or elegant or advanced. It's always going to be something easy. Yes, but if you have contour lines, obviously, that have different slopes and things like that, you're going to get, this thing is going to be an equation itself. So that's kind of obvious. Yes. So we have two basic understandings in the past couple of videos. We started with the total differential, which I think was 2.2, and we just go through the understanding of contour lines, and then it basically ends with this equation right here. We can kind of pause the video here if we want to read. I'm not going to read it because they basically just state everything that I said. Yeah, so I'm just kind of thinking about the next video. We just did this. We don't really have to read this. They're really just doing an example and talking about what I said. In fact, they do the same exact example right there, and they get negative 1/2 or negative 0.5, just like we did. It is okay to do maybe something a little bit more fancy like the Cobb-Douglas. So we can do that example. We'll just skip it. Yeah. It is the same thing, but we're starting, my thoughts are kind of dwelling. If I read, my thoughts are kind of dwelling right here. Now consider the Cobb-Douglas function. We don't have to do it there, but if we take the partials and we plug into our equation, so you could do the thing there, yes. And it's a Cobb-Douglas function, which down below we see it's going to be a little bit more difficult. So of course, this time it does equal an equation. Negative 3x2 over 2x1. That's going to be an equation for the slope of all the contour lines. So it's actually a really cool understanding, yes? Yes, very obvious. I don't mean to dwell, but this equation gives us the slope. You just do one partial derivative divided by the other, the negative of it. And yeah, so we can read this if we want to right here. They just give us the contour lines of the Cobb-Douglas. Then we move into 2.3 optimization.